thanks a lot for being here first. And well, let's start by talking about game development programming requirements. Well, usually the fact is that game programming has a completely different set of requirements from the, let's say, usual enterprise programming. One of these, for example, is that you have really lots of objects to be managed at the very same time. Like see in the screenshot, you have hundreds of enemies charging at you, bullets flying everywhere. You may have potions around. You may need to do some resource management for maybe an RTS. And so you really need to think that whenever you're talking about managing entities, it's not managing 10, hundreds of entities. They may get to 1 million of entities. And so you usually have some problems already in there. The second requirement is the fact that you need to give an immersive feeling. Well, if your game sometimes lags, well, that's bad enough. If it consistently lags, well, that's way worse. If it lags to the point of freezing, of being completely unresponsive, well, you see the reaction your player will have. And the fact is that in game programming, 60 frames per second is a dogma that you absolutely don't want to break. And if you take it a little bit from a step backwards, it means that in less than 20 milliseconds, you need to recompute the entire state of the game often. And I mean, in these 20 milliseconds, you need to prepare for rendering, perform movement, maybe perform pathfinding, AI stuff. It's really kind of complex at this point. And the fact is that it's not really a requirement that you usually can skip. I mean, you can have the fanciest graphics, you can have the most funny mechanics or the most wonderful story ever. But if your game lags so bad that it freezes, well, let's say that it won't be remembered for that. Absolutely. And also because, as usual, since you have some fixed time in which you can do all your stuff, if you manage to shave off some milliseconds out of them, it means that you can just put some more features, some more funny features in your game. And actually, one problem that often is met when doing this kind of programming is that if you go for a, let's say, naive OP approach, well, it is often not enough. One problem is that OP is specifically tailored for working at a single entity level. It's not tailored for doing bulk stuff at once. And yeah, you can do, of course, some optimization, but honestly, yes, they definitely help, but not so much. And well, kind of optimization that you could do are, for example, well, you could switch the algorithm. Maybe you don't need to have the exact solution, but maybe just use a greedy algorithm. You may use caching to improve performances. Well, unless you're on a console, you could also throw some more cores at the game. Then you would be fine. And any of these solutions will help. But the question is exactly why do we have speed issues, performance issues at the first time? Well, if you look at the various solutions that you have, basically they all just gravitate around, let's say, main guilty party, that is the CPU. And the CPU, actually, there is a very wrong assumption that is done, let's say, regularly by humans. And that is that the CPU, when it has to get some data from the RAM, reacts like this. That's not the case. Usually the, let's say, most similar reaction is this one. Yeah, I'll do it, crying. And the reason for that is because of access time. Now, if you take it from a human perspective, RAM access is really, really fast. It's blazingly fast. On the contrary, for a CPU, well, it is painfully slow. I mean, for a CPU, if it takes, let's say, 1 hour to perform something, having to get the data from the RAM means that it basically has to take a long weekend vacation before finally getting it. Well, if it gets it from the hard disk, it's a century worth of vacation. So yeah, it's a matter of perspective. But the meaning is that when looking at RAM, humans and CPU compare it to two different things. The human compares it to the access disk, and it's blazingly fast in that case. On the contrary, CPUs compare it with the cache. Now, our computer, let's say, they usually have the very same kind of memory organization. At the top, you have your RAM. Then the further you go down, let's say that the CPU is right at the bottom. You have some caches, and they are always faster, but also always smaller. And basically, the CPU will work only with the smaller ones. So basically, the data cache or the instruction cache. And you can see it from, these are actually the specs of my notebook. RAM, huge. Data cache, the level 1, so basically the data that the CPU will actually work with, 64 kilo. That's really, really small. And the fact is that whenever your CPU tries to work on some data, it will first look at the first level cache. If it's there, okay, fine, we're going at the maximum speed. If it's not, that's what is called a cache miss. And that's something that you really want to minimize in case you are trying to program for speed. So what happens in case of a cache miss? Well, it looks for then at the level 2 cache, which is way bigger, then L3 cache, and then, well, too bad, I have to go to the RAM. But exactly how bad is a cache miss? Well, it is actually pretty bad. Now, if you look at the right, there is this very simple example. I just did a matrix traversal. First by row, the blue line, and then by column. Now, the operations are exactly the same. You can see that as the matrix size increases, well, the results are way worse. Here, more at the beginning, they are almost identical. And the reason for this is that basically, if you have a very, very small n value, well, it will find, even by going by column, it will already find it in one of the caches. So basically, it's something that escalates. Really, they are completely, I think, asymptotically complexity. And the fact is that for this, the CPU is organized in such a way that it really loves to work with contiguous data for the cache misses, and also in predictable patterns. It has no issue in jumping around as long as there is always a pattern. So basically, you can do prefetch, you can do branch prediction, and whatever. And one nice corollary of this is that, for example, if you have a primitive array, so think about array of int, usually, as long as the array is not so big, it is faster to just scan for a value than to go through a binary tree, for example. Why? Because it does it really sequentially, really, really fast. On the contrary, on the B tree, you may have to, let's say, resolve pointers, the reference, and jump around. So that's why you usually try to keep arrays small and then escalate when stuff increases in size. And well, now that we are more or less clear what is a cache miss, what happens in video games, why it is a problem in video games. Now, for reference, suppose that you have this monster class. It has a lot of fields, may have name, 8 points, magic points, it may have a drop table, really a lot. Keep it for reference. And again, if this is just a flattened view, in case you have, let's say, subclasses inside, so basically subcomponents, performances may take a hit just due to having to the reference pointers. It usually is not the case, but in some pathological case it happens. And well, you see the problem in the event loop. Basically, most of the games, if not all, have this loop that just cycle endlessly, in which, well, these are just two examples of the, let's say, main strategies to manage this. You have first, well, player does his stuff, and then you do all operations one monster at a time, which has its own problem because then interaction between monsters become kind of complicated. Otherwise, there is the second approach that is basically for all monsters, you do one single operation of time. First, for example, you update the state for everyone, then you move everyone, then you try to attack whatever it is, and then you render. And again, how do you think that the CPU will react when having to manage this? Well, pretty easy. Again, well, the reason for that is that if you get a look at how the data is stored in memory, well, contiguous colored blocks are the same entity, while same colored blocks are a specific field. For example, yellow may be, I don't know, the hit points. Red are a temporary status that is actually available just on one entity. And if you look at it, especially for the second approach, well, we need to process every time the yellow block. We are jumping everywhere. Jumping everywhere, cache miss, bad. And to solve this problem, which there is what is called the ECS, which is actually, as you may have guessed from the name of the whole talk, what I will be talking from now on. And ECS is actually an architectural pattern. So basically, it prides itself on, let's say, 2 + 1 pillar. The first one is the locality and coherence of data. So basically, it solves, let's say, it mitigates the cache misses problem. And it achieves it by basically storing related fields all together in memory. No problem what the entity we were talking about. Then there is the fact that it really makes it easy to have, let's say, dynamic data / behavior at runtime. And well, the third one, I'm not really so sold on that, but basically it claims that it eases reuse and bug minimization. Now, that is true, but instead of ease of reuse, I would just call it ease of pluggability. You switch the game, you have, let's say, your components, then it is easy just to switch, bringing them back as they are, no modification. So basically, it's not really like a framework, it's more just a plug and play. And well, ECS is an acronym, and it stands for its three main building blocks, which are well, the entity, the component, and the system. Entity is pretty easy. It's exactly what you think it is. Component actually is the equivalent of the fields that you had in the monster class before. And the fact is that they are just, well, think structs in C. No behavior at all, just plain data. And the systems, well, it is, you need a place in which to do stuff. And system is exactly where they are. And basically, it's they are the parts that are responsible for updating the state of the game every single frame. Now, some examples. Well, entity, player, medikit, a log tree, maybe in specific case, a particular tile, maybe an entity. Component, well, it's just some fields. So both health, you may put the bounding box or the speed or particular status in the components. And for system, well, the more frequent ones are the AI system. Then you have the collision detection system. You can have a status system. You can have really whatever system you want, depending on your use case. And well, just some guidelines here, because they kind of go against, let's say, the normal guidelines. First one is completely forget inheritance. Use composition everywhere. Why? We need speed. Using inheritance often goes through the vtables, and you don't want to go there. Access to vtables is painfully slow. Mutability. Again, immutability is great, we all know, but memory allocation are costly. You need to change components on the fly. Components, of course, should be small, mainly because, well, you're trying to fit, to minimize cache misses. So basically, the more components may be in a single cache line, well, the faster it will go, obviously. And the last one is when managing components, Well, you should use arrays, because often in most languages, they are the only structure that is guaranteeing you that you will have them consistently, contiguously in memory. Again, you may have two different approaches, AOS and SOA, but for now, let's dive a little bit more in detail in the single blocks ones. So the first one is not the entity, but the component. That is actually the building block of the whole pattern. So again, things about mutable value objects, things about them as being structs. Usually you assess them in bulk, and you go through them through dedicated component manager. Now, the component managers are the ones that are actually responsible for ensuring that everything is contiguous in memory. You may have two different approach. The AOS one, that is basically stands for array of structures. So imagine that you have your position component, let's say, X and Y fields. In memory, you would have X, Y, X, Y, X, Y, X, Y, all contiguously. The other approach that is a little bit more drastic is basically split all the fields of a single component into its own dedicated array. So again, position component, X, 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 then Y, 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 Y. Again, they both have their merits and their drawbacks. It really depends on your use case. Usually, if your component, for any reason, has some flags, you go with the structure of arrays approach, because at that point it will be way easier and you can, again, fill more of them in a single cache line. The other one is the entity. Entity is kind of difficult to define. And let's say that in implementation-wise, they usually are just some kind of glorified integers. Think about primary keys, auto-generated primary keys, or a sequence in databases. And again, they do not have anything inside them. But in theory, they should also only have components. In practice, they don't have even them, because again, when you need to assess them in bulk, it's way easier just to pass through the component managers. Again, the last one is the systems that are the system that actually are the real, let's say, workhorse. And well, they are kind of easy conceptually. You have some components in, you update some other components out. Nothing more. They usually tend to work in complete isolation. So if you have, let's say, the collision detection system, it is completely oblivious to the existence of a movement system. So they tend to be quite simple in structure. And that was why they were saying, yeah, it's easy to have less bugs on there. Components are so systems are so simple that you usually don't have many problems in there. The problem is that orchestrating them is a mess. Every time, one of the most complicated things that when you write your game loop is, okay, which system goes before which other one? Because, for example, movement and alpha update systems, well, depending on where you look at it, sometimes it makes sense that the alpha comes before the movement. Player is dead, cannot move. Sometimes it makes sense that the movement comes first before the update alpha system. You step on a burning tile. Those are very trivial examples. And to look at how they work all together, well, suppose that we have a very simple system, the poison update system. It gets 3 components. 2 of them will be the input ones, poison one and the resistance one, and the output will be stored in the F component. Then what it just asks is someone provide me all the entities that have these 3 components, all these 3. For any one of them, gets the data, computes the damage, then updates the F component. And if you look at how the CPU processes here on the right, the single components, let's say that on the left, you have your component array, and sorry, on the right, on the left, on the rows you have your component array, and on the columns you have your entity ID. So basically, first one goes together with the third one and the fifth one. And if you look at how the CPU will assess this data, you will see that they will be assessed like this. This is something that is extremely cache friendly, assessing completely contiguous data in a very predictable way. For the CPU, there is nothing better than this, honestly. Now, apart from the three main building blocks, we have, let's say, two blocks that are not strictly necessary for the pattern itself, but they are really, really useful. So it's kind of, doesn't really happen often that you don't have neither of two. So the first one is, again, the word. Basically, when I said before that someone will provide the system with use the components or use the entities, he is exactly the one that does that. Otherwise, you put stuff in the game loop, but it really becomes a tangled mess. And is also in charge of creating entities, destroying components, updating other stuff. So basically, it's, say, a top-level orchestrator. The second one is the so-called event system. Now, it's a system, but not in the ECS sense. It is there just to keep a system even more isolated. Now, think about movement system. Player is falling down. If it falls long enough, if it crashes to the ground, well, you would want to update the health in some ways. Player got hurt, at least. And yeah, you could give the health system and the movement system the rights to update the health component, but does it really make any sense? They're completely uncorrelated, so nah, I wouldn't do this. And for this, there is this event system, which is actually just an event bus in which you subscribe and you publish some stuff. Like in this case, it would be just a decrease player health by 80%, like this. Then next step, it will be processed by the dedicated system, the one that is registered to that. Now, ECS obviously helps in some cases. There are some cases in which you do not want to use ECS. Well, it is designed to process stuff in bulk. So when you don't really have so much stuff that you need to process in bulk, like you have 10 entities, come on, don't use ECS. It's complicated to have one running. Just go for the usual OOP or whatever you prefer approach, and it will be more than enough. Or when you, for any reason, need to access the CPU, the disk a lot. I mean, going back to the analogy of 1 day for 1 hour, 4 days, we're trying to shave like 2 hours, but then we're not comparing about the 4 days. We're comparing against the whole century worth of vacation that the CPU has while waiting for the data. Not worth it. I mean, ECSs are so unless you really have a huge case for it, do not use it. Or in some cases, go for a hybrid approach. Maybe game loop is written through an ECS. Inventory management, it's not. It will be a little bit more complicated to interface them, but again, it won't be completely impossible. Again, since data and code are completely uncorrelated places, maybe you don't want that. You want to have them all together. And just don't use ECS. It would be an anti-pattern in that case. So this kind of help ends my presentation. Now, if you want to go home without having heard anything about my presentation till now, these are the major key points. So basically, in game dev programming, what you want usually is speed, and what you achieve and how you achieve it. Well, one of the ways is try to be as much as cache friendly as possible. There is this pattern, architectural pattern, ECS, that actually does exactly this. It keeps different components in very contiguous memory locations. It is built upon, let's say, components where data is, entities that groups them, system that operates on them, and the stuff, again, remember, you don't have any silver bullets. Sometimes you made it, bulk speed, bulk jobs, fast, then it's fine. Other stuff, just don't do it. And that's basically it.